Hi everyone, welcome back to Math 112. This is Scott. Let's get started. What we're going to be doing today is looking at sections 8.5 and 8.6, which are both about vectors. And in 8.5, what we'll learn about is what's called the dot product. So the dot product. All right. So first off, let's just launch into it. The dot product. Also called the scalar product. Of two vectors. Let's say v equals ai plus bj and w, which equals ci plus dj. It's written v dot w. So it's a multiplication of two vectors, and it is written with a dot, and that's why it's called the dot product. There's another way of multiplying vectors. We're not going to really get into it in this course, but you may see it. It's called the cross product, and in that, the multiplication is written with the little cross. Okay, written this is given by, now here's how you actually calculate it. Oops, v dot w is equal to a times c plus b times d. So no vector components are left, it's just a number. So this produces a number. So it just produces a scalar, that's why it's called the scalar product. All right. There is an alternate formula which is that v dot w is equal to magnitude of v times the magnitude of w times the cosine of theta, where theta is the angle between them. So this is the angle between v and w. So in other words, if v looks like that and w looks like that, this would be theta. Now theta can be more than 90 degrees, but it has to be somewhere between 0 and 180. But we can put these two things together to find the angle between two vectors given their components. We can use these two formulas to calculate the angle between two given vectors. So in particular, if v dot w is equal to the magnitude of v and the magnitude of w times the cosine of the angle between them, we can just solve this for the theta. So it's equal to v dot w divided by the magnitude of v times the magnitude of w, which means in turn that theta equals cosine inverse of this same thing. Now, there are some special cases for special angles in relation to each other. So special cases. All right. So first, let's say the case of what are called orthogonal vectors. So these are vectors that are perpendicular to each other. So what does that mean? That means theta equals 90 degrees. And if theta equals 90 degrees, well, what's the cosine of 90 degrees? That's 0. So v and w are orthogonal. The word orthogonal, it literally just means the same thing as perpendicular. It's just in Greek rather than Latin. Ortho means right. For example, orthodox means having the right beliefs. And then gon means angle. This means right angle. So v and w are orthogonal if and only if v dot w equals 0. It's just the number 0. Parallel vectors. So parallel vectors are vectors where the angle between them is either 0 or 90 degrees, or in other words, pi. So, either 0 or 180 degrees, I'm going to say. So these are, so the angle is either 0 degrees or 180 degrees. And what this means is v and w are parallel if one is a multiple of the other. All right. So let's see. Let's just put in some more facts, and then we can start to actually try some examples. So other facts. All right. So some other facts that will come in handy will be this. So for any vector v, if you do v dotted with itself, that equals the magnitude of v squared. Okay, duly noted. Let's see. So this is going to be true of any vector v. Also. All right, the camera just cut out there for a second, so let me catch you up with what I was writing. So decomposition. So we can decompose a vector if we are given a vector and another vector. So decomposition. If we are given a vector v and another vector w, we can decompose, and what that means in this context is rewrite as a sum v into two pieces. So we can decompose v into two vectors. v1, which is parallel to w, and v2, which is perpendicular to w. So the words for each of these are, this is the vector projection of v onto w, and then the perpendicular part is called the orthogonal complement, but you don't need to necessarily know that right now. Now here's what that would look like if we had it as a picture. So let's say we had our v going just this way, and let's say we had some w that was going off in this direction. Okay, now what that would mean is I can re-express v in terms of v1, which would lie in the same direction as w, and v2, which would be exactly perpendicular to w. So in other words, if I rewrote it like this is what v1 would look like. v2 would look like this. You add them together, and they make up the original v. And these are orthogonal, or perpendicular to each other. Okay, now here's the recipe for the v1s and the v2s. So v1 is equal to, the way you do it is, if you look at this shape, what we've really got here is a situation where we can take the cosine of the angle between them. But how can you take a cosine? One way is by taking a dot product. So if you don't know the angle already, then we can just take the dot product, and the cosine of the angle between them will become available. So v1 is going to be equal to v times the cosine of this. So that's already partly there. But then we if we multiply that times w, that'll give us an extra bit, and then we have to scale it down a little bit by doing this. So you don't have to necessarily understand all the ins and outs exactly of this formula right now. The important thing is that it's going to turn out to be very, very useful to us. But you should be able to make sense of it all in terms of cosines and the Pythagorean theorem and things like that. Okay, so v2, on the other hand, is going to be equal to what's left over of v1, of v, if you subtract v1. So v2 is equal to v minus v1. All right. And then the reason why we often do this is because we frequently want to decompose a force into two different forces in applications. Applications. We will use this decomposition to find the components of a force that have a specified direction. All right. Another application is the application of work. So work. So the work done by a force that's acting at a certain angle, it essentially refers to the net amount of energy change that is accomplished by that force. And that energy change can mean a change in potential energy, or it might mean a change in kinetic energy, something like that. So the work done by a force is a result of the force and the displacement. And when we apply a force, which force is a vector quantity, so we will always write it as a vector, a force F along a displacement, which is also a vector quantity, V, the total work done, in other words, the amount of energy change. Here, typically it'll be a matter of potential energy being changed. The total work done will be F dot V. All right. Now, this was all just us describing how these things all work, and now let's actually see all these things that we've been discussing in examples. All right, to begin with, we will be given a couple of vectors and asked to compute their dot product, and then find some things about them. So, let's say for these, find v dot w. Calculate the angle between v and w, and then the final thing is determine whether they are parallel, orthogonal, or neither. Parallel, orthogonal, or neither. All right. And just to start, we will just take vectors such as this. So A, V equals I plus J. W will equal negative I plus J. All right, so let's just think about this. So first off, V is just going to be like 1, 1. If I thought about it like coordinates, and W is the same as negative 1, 1. All right. Well then, V dot W equals, just multiply first component with first component. That's 1 times -1 plus 1 times 1, which equals -1 plus 1, which equals 0. Well, that's interesting. So if the dot product of these vectors is 0, then, therefore, the angle is 90 degrees, and the vectors are orthogonal. I didn't actually need to calculate anything here. Once I had the dot product, I already could tell that the angle would be 90 degrees and that the angles in question would be orthogonal to each other. All right, let's try another one. B. How about V equals 2I plus 2J? And W equals I plus 2J. So just 1I plus 2J. Well then, once again, if I choose to break it down into angle brackets, just to make it, just to jog the memory, then we have this. And then V dot W is equal to 2 times 1 plus 2 times 2, which is equal to just 2 plus 4 is 6. Okay, well, that's not equal to 0, and I can see that V is not a multiple of W, W is not a multiple of V. So, so what that means is I have to actually just crunch the numbers to find the angle between them. So it's not orthogonal, doesn't seem to be parallel. So therefore, I will have to find the magnitudes of the V and the W. That's 2 squared plus 2 squared, the square root of that. That's 4 plus 4 is equal to square root of 8. In other words, is equal to the square root of 4 times the square root of 2, which is equal to 2 root 2. Good to know. As for W, that's equal to square root of 1 squared plus 2 squared, which is equal to the square root of 5. Okay? Well then, what I know is that cosine theta is equal to V dot W divided by magnitude of V, magnitude of W, which equals 6 over 2 root 2 times root 5 is equal to 6 over 2 root 10. I can cancel the common factor of 2 that they share. So 3 over root 10. And so then theta equals cosine inverse of that. Now, if this were a known angle here, then I would be able to perhaps just say off the top of my head what it equals, but it's not, so we'll have to calculate. So let's see here. So first off, check your calculator mode. Degrees would be slightly preferable here. Radians would be perfectly reasonable, but we're going to default to degrees here. So cosine inverse of 3 divided by square root of 10. And that gives me 18.43 degrees. Round whatever seems appropriate in the circumstances. If it's a problem from Pearson, then I'll tell you how they want it rounded. Otherwise, just round as reasonable. Remember, degrees are already pretty small, so if you go to fractions of degrees, that gets quite precise. Okay, so that's the angle between them. And this angle is not 0, it's not 90, it's not 180. So these two vectors are neither they're neither parallel nor orthogonal. V and W are neither parallel nor orthogonal. All right, now let's try another one. And here we'll have a V and W as follows. So V equals 1 plus root 3 J, sorry, 1I. Let's make that an I plus root 3J, and W equals I minus J. So then V would equal just 1 root 3. W would equal 1 negative 1. V dot W would just be 1 times 1 plus root 3 times negative 1, which will be equal to 1 minus root 3. Okay, so be it. Now then if I want to, so this is not 0, so we can't draw any conclusions. And it's clear that neither of these vectors is a multiple of the other. And so what that means is that we're just going to have to crunch the numbers here and see what we get. Okay, so the magnitude of that is going to equal square root of 1 squared plus root 3 squared. In other words, 1 plus 3. In other words, square root of 4, which equals just 2. As for W, this is going to equal square root of 1 plus 1, or 1 squared plus negative 1 squared, which is going to be square root of 1 plus 1, which equals just root 2. So then what that means is that that cosine theta is going to equal 1 minus root 3 divided by 2 root 2. Now, if this had been something that was a little bit friendlier, we'd be a lot happier about it. But as it is, it's quite ungainly. And so what we'll just say is that theta equals. So you might try rationalizing the denominator and seeing if that helps you. But you're still going to end up with things that are not necessarily going to be the friendliest things available. And so we'll just go cosine inverse of this and just let the math work itself out. We have suspicions that maybe this would be something clean and tidy, but it's not going to be quite one of our exact friends. It's going to be some twist on one of our friends. Okay, so cosine inverse, I have to be careful here. I have to put parentheses around the entire numerator. Root of 3. So I had to put parentheses around the entire numerator, otherwise there would be an error. And I have to put parentheses around the entire denominator as well. So make sure you're very careful here that you are entering into the calculator what you intend to be. So, and we get 105. Now 105, that is of course one of the angles that we could have found with our knowledge of the unit circle and the sine addition and or in this case cosine addition formulas, but we can also just calculate it this way. So the vectors v and w are neither parallel nor orthogonal. All right. How about something like this? V equals 2i, minus j, and w equals uh, equals negative 3i. No, sorry, I mean a negative 6i plus 3j. Okay, you can look at this and you might already start to have some suspicions, but we'll just stick with the plan. We'll just do this by normal means. So v equals 2 comma negative 1. W would equal negative 6 comma 3. And then v dot w is equal to 2 times negative 6 plus negative 1 times 3, which is going to be negative 12 minus 3 is going to be negative 15. Okay, interesting. Now, if we calculate the magnitude of v, let's pretend like we don't notice anything special about these two vectors. It's going to be 2 squared plus negative 1 squared, which is going to be equal to root 5. Okay. Magnitude of w is going to equal square root of negative 6 squared plus 3 squared, which is going to equal, it's going to be 36, and it's going to be plus 9 is 45, which is equal to root 9 times 5, which is equal to 3 root 5. And so then what we have is cosine theta equals negative 15 divided by root 5 times 3 root 5, but root 5, that's the same as root 25. In other words, just equal to 5. And that equals just negative 1. So that means that theta equals cosine inverse of negative 1, and we know actually pretty well that the cosine inverse of negative 1, just according to the unit circle, is going to be equal to 180 degrees. So that means that v and w are parallel. All right, so that's what it looks like when all we are given are just a couple of vectors given in their component forms, and we want to figure out the angle between them. But now, let's look at what this looks like in the context of some applications. All right, so first example will involve work. So this is work in the physics sense. So find the work done by a force 6 pounds acting in the direction (30° to the horizontal, and moving from 0, 0 to 3, 0. Okay, so let's sketch some of the things going on here. So first off, 0, 0 to 3, 0. So this is where we start, and then this is where we end. Okay, so that means the displacement which is going to be the change in the x for I plus the change in the y for j is just going to equal 0 on the I, 3 on the j. We can see how much the y is changing. It's changing 3, and the x isn't changing at all. I mean, the other way around. What am I saying? The other way around. The other way around. I mean, 3 on the x and 0 on the y. Okay, so in other words, v just equals 3i. Keep on stuck. My mind is stuck on it being a j, but it's an I. Okay, so that's going to be the displacement. Now, as for the force, it's 30° to the horizontal, which means 30° off from the horizontal. So here we can write it like this, and we aren't actually told whether it is off in the direction of up or off in the direction of down, but it turns out it doesn't really matter. It will be the same amount of work either way. So here, this is the magnitude of the force. This is the 30° angle, and so what we really want here is F dot V. Now, this is actually a situation where what we have is actually perfectly designed, not for the component by component meaning of dot product, but actually the angle between them dot product, where F here has a magnitude of 6 pounds, V has the magnitude of 3 feet, and this is just like times. And then cosine of the angle between them, cosine 30 degrees. So we're told 6 pounds, we're told 3 feet, and then cosine of 30 degrees is root 3 over 2. So that's going to equal 18 root 3 over 2, which then is just equal to 9 root 3, which if we evaluate it is approximately 15.588. So I'll say 15.59, and the units here are they're called foot-pounds, because the units here are a combination of feet of displacement and pounds of force. In metric units, the unit of work would be the same as the unit of of energy, which would be a joule. That's Joule. Okay, so it's an example. And here's another example. This is of a different sort. This is an example called of a problem called braking load. Okay. So a car with a gross weight of 4,500 pounds is parked on a street with a 10% grade. And that means slope. I mean, a 10 degree, I should say. Sorry, a 10 degree grade. So that's the same as a slope here. So find the magnitude of the force required to keep the car from rolling down the hill. So that is so the street is angled, and we want to make sure that the car doesn't fall. So we need to know how much force the brakes have to apply, basically. Also, find the magnitude of the force perpendicular to the hill. All right. So what we need here, first off, is a diagram. So the situation here is that we've got a street that is at a 10 degree angle. We've got a car. So we're not going to draw it too precisely here. And that car has a weight of 4,500 pounds. And weight means going just straight down towards the center of the earth. Now, the question that is asked is basically to find basically the magnitude of the weight that's going this direction. So we want this and this. So we want to know how much force is the car applying in its attempt to roll down if the brakes weren't holding it back. And then the other direction is this. So what we are really trying to do here is resolve. Resolve the vector into two perpendicular parts. All right. Well, let's think about this. So first off, let's just say that V here, which will be the weight, is just the 4,500 pounds, and it's in the direction down. So it's just going to be negative J. So here, it's right over here. So the weight, negative, to mean down, 450 J, and then W, which is going to be basically just like the street or the hill. So this is equal to, so it's just equal, you can think of it as just being cosine of 10 degrees I plus sine of 10 degrees J. So this is basically a unit vector. That's parallel to the street. All right. Well then, V1. So this is going to be the component of V that's parallel to the street. And that's equal to the V dot W over the magnitude of W squared times W. Which is equal to negative 450J dot product cosine 10 degrees I plus sine 10 degrees J divided by the magnitude of W squared times W. Well, taking this piece by piece here, 0 times cosine 10 degrees is just going to be I. And so that means what we're just going to have is 0 plus negative 4,500 sine 10 degrees for the J parts. And this is a unit vector, which means that its magnitude is just going to equal 1. So that's just going to equal 1. And then times cosine 10 degrees I plus sine 10 degrees J which is just going to equal negative 4,500 times the sine of 10 degrees. So it's going to be negative 781.4 cosine 10 degrees plus negative 781.4 sine of 10 degrees for the J. And then if I want the magnitude, which is what the problem after all asks for. The magnitude of v1 here is going to be just the part that is, actually, let's just evaluate this. It's going to be based on the formula for magnitude of vectors, but it'll be easier if I just do this. If I just evaluate these pieces, so 781.4 cosine 10 degrees equals negative 769.53 I, and then minus the same thing but with a sign, negative 135.69 J. So then if I want the magnitude of the V1, then what I can do is just take the square root of the squares, and get a number. Okay, so what do we got here? So square root negative 769.53 squared. I'm careful about my parentheses when there are negatives involved here. Negative 135.69 squared, and then that's the end of the square root. That equals 781.4. Now, okay, so this is the magnitude of that, and that's going to be then pounds. Now, it just so happens that that is the same as this over here, and that's because this was a unit vector. If we were more knowledgeable about some of the properties of magnitudes, then perhaps we would be on our toes and we would recognize that the magnitude of this vector is in fact going to just equal that 781.4, but we don't have to know that. You can just calculate it by brute force here. Now, V2 is equal to V minus V1, which is going to be negative 4,500 J minus, and then V1 we found was negative 769.53 I. Oops, don't end those parentheses yet. Minus 135.69 J, which would then equal, on the I side, just positive 769.53. And then on the J side, it would equal, it looks like, be negative, and here let's not be 45, negative 4500 minus negative 135.69. Don't make any silly mistakes. So 3134.31 J. Okay, so that would be the vector for V2. This is the part that is perpendicular. to the hill. This is what's called, by the way, the normal force in physics. Oops, sorry, it's perpendicular to the hill. And then if I want the magnitude of the V2, which is what the problem asks for, I would just have to do the square root of the pieces and calculate that. So 769.53 squared plus negative 3134.31 squared. And then we can just calculate away. I don't need any parentheses on the first one because it's not negative. One, 34.31 squared and the square root. And that gives me 3227.39 pounds. And you would just round according to whatever information, whatever was being required of you. All right, and then one more example of a very similar nature would be something like this. If you want to hold, this is an example. This one is called ramp angle. So if you want to hold a heavy load on a certain ramp, this you can just figure out what the force would be necessary to push on it. So what force is necessary to hold a 200-pound object at a 20-degree incline? Without it slipping. So in other words, we've got a 20-degree ramp. We've got a 200-pound object. And we want to figure out this force. I want to figure out how much force the 200-pound object is pushing down the ramp, and then we just have to push back. All right, well, let's figure it out. So V, which is the weight, can just be the negative 200 J. And W can be the unit vector. Along the ramp. This can be W equals, and it's just going to be cosine 20 degrees I plus sine 20 degrees J. Then what we want is only the V1 here, which is V dot W over the magnitude of W squared times W. And we want really just the magnitude of V, because it says what force is necessary, and so we can just say what the magnitude of this will be. Okay. Well, let's see what this would equal. Negative 200j dot cosine 20 degrees I plus sine 20 degrees j divided by the magnitude of w, but it's a unit vector again, so magnitude of w just equals 1. And w is, of course, the cosine 20 plus sine 20 thing, but let's just calculate this part first. So this equals 0 on the I part, and then negative 200 sine 20 degrees for the j part. And then what do we have here? So it is negative 200 times sine of 20 equals negative 68.404. And then here I might as well evaluate the cosine of 20. 0.93 940, I guess. Let's write it again. Minus 68.40, 0.9. 940 I sine 2342 j. All right, 0.940 times the negative 0.6840. Sorry, negative 68.40, I mean, equals negative 64.296 I, and then same thing, 0.342, negative 68.4, negative 23.393 j, and then if we want the magnitude of the force, V1 would be equal to, and again here, if we know more about vectors, perhaps you already know what the answer to this will be, knowing that W is a unit vector. But if you don't, then this calculation is going to still get you to where you need to be. So square root of negative, parentheses, negative 64.296 squared plus 0.29393 23.393. I forgot to put in the negative that squared and you get 68.41 or 68.4 roughly, and that's how many pounds. All right, now for the last topic of the day, we can look at section 8.6, which is called Vectors in space. And space here means 3 dimensions instead of 2. So the idea we can do the same vector operations in 3 dimensions, i.e. space. So space in math refers to three-dimensional world instead of a plane, which is a 2-dimensional world. As we did in 2 dimensions. And the way these things are typically represented is using what's called the right-hand rule. You have the x-axis, you have the y-axis, and if you swing your fingers from the x-axis to the y-axis, the direction that your thumb is pointing on your right hand will be the direction of the positive z-axis. So the way this is typically represented is like this. And what we can do is you can have vectors in this space, and they will be represented not by 2 components, the I and the j components, but by 3 components. So we can write these vectors in the form v equals ai plus b times j plus c times k. So this represents the z component. This is the y component. And the first term represents the x component. All right, so first things first. Let's see, so position vectors. Position vectors. So here, once again, so i.e. displacement vectors again. We can just say that the vector is equal to change in x in the I direction, change in y in the j direction, and then just change in z in the k direction. Magnitude. The magnitude of v is equal to the square root of its a squared plus its b squared plus its c squared, where v equals ai bj plus ck. So where a, b, and c are standing for, by default, the x, y, and z components, then it is essentially the same formula as it was before, just with an extra term. And then Putting those two pieces together, we get the distance. So the distance between 2 points. This is the same as the magnitude of the displacement vector between them. By taking the magnitude of the displacement vector. So for example, let's say I wanted to find the distance between a couple points. And those points were, let's say, P1 equals -1, 2, -3. And P2 is equal to 0, -2, 1. Well, first off, V equals, and this is just the displacement vector, so it's going to be negative, I should say, V equals change in x times I plus change in y times j plus change in z times k. Let's just establish our formula first, and now put in the pieces. So the change in x, so that's new x minus old x, so it's going to be 0 minus -1, -2 minus 2, and 1 minus -3. Gotta be careful about our negatives here. So it's going to be just 1i, going to be minus 4j, and that's going to be plus 4k. Okay, now if we want to find the magnitude of v, that's going to equal square root of, so a is 1 here, so it's going to be 1 squared, -4 squared for the b, and 4 squared for the c. So it's going to be 1 plus 16 plus 16 is square root of 17. No, sorry. 17 plus another 16. Square root of 33, I mean to say. Okay. And if you can do one of these, you can do a million of them. So that's enough from that one. Now, let's try another example. Find the position vector for the vector with initial point. Let's say it is 3, 2, -1. And terminal point. 5, 6, 0. All right, well, once again, v equals change in x, I, change in y, j, change in z, k. So it's going to be x minus x is 5 minus 3. Y minus y, 6 minus 2. Z minus z, 0 minus negative 1. 2i plus 4j plus k. Now, let's see, another thing we can do, which we could do before with regular vectors, would be just finding their magnitude. Find the magnitude of v. V equals, let's just say, negative 6i plus 12j plus 4k. Magnitude of v is equal to square root of the first component squared plus the second component squared plus the third component squared. So that's going to be 36 plus 144 plus 16, which then equals 296. Now, if you are suspicious about a number like this, you can plug it in here. Oops. You can plug it into a calculator. 296. Oh, sorry, I mean 196. 196. And you can find that that actually happens to equal the exact number 14. If it weren't exact, you would want to pull out whatever perfect square you could from it and simplify it that way. But if you get suspicious, then you can pull out whatever common factor you can. All right. Now, let's say we had something like this. Let's say that that v is equal to 3i minus 5j plus 2k, and w equals negative 2i plus 3j minus 2k. Let's say that given these, we were supposed to be finding something like v minus 2w. All right. So then the way that's going to work is you would just take the components of v and the components of w, and you would just put them basically together according to this recipe. So you could actually just distribute this. So plus 4i minus 6j plus 4k. And then you could essentially just combine like terms. That's what adding it component by component really amounts to. So it's 7i minus 11j plus 6k. And then maybe you would want to find something like the magnitude of v minus w. Well, let's just first unpack what that actually means. It's 3i minus 5j plus 2k minus negative 2i plus 3j minus 2k. So what's that going to be? That's going to be the magnitude of 3i minus 5j plus 2k plus 4i minus 3j plus 2k. Then you can combine the like terms. 7i minus 8j plus 4k. And then that equals the square root of 7 squared plus negative 8 squared plus 4 squared, which is so that's equal to square root of 7 squared plus 8 squared plus 4 squared, 129. Now 129, if you were curious as to whether that had any perfect square factors in it, well, you can think off to the side. 129. Well, it is divisible by 3. I can tell because its digits add up to a multiple of 3. So it's going to be 3, and then what's it going to be? 43. And I can see that there aren't any perfect square factors here. So there's nothing I can do on this. I'll just leave it as the square root of 129. And then one more type of thing you could do here would be just something like C magnitude of V plus magnitude of W. So this would mean just essentially evaluate it in two parts and then put them together. So magnitude of V would equal square root of 3 squared plus negative 5 squared plus 2 squared. So if we look at what V was, these are the components. The magnitude of W would be the square root of negative 2 squared plus 3 squared plus negative 2 squared. Okay, so this one right here is just going to equal 9 plus 25 equals 34 plus 4 equals 38. this one over here is going to equal just the square root of 4 plus 9 is 13 plus another 4 is equal to 17. And so what we're going to have then is that the magnitude of V plus the magnitude of W equals root 38 plus root 17. All right. Well, if we can find magnitudes, then we can also find unit vectors that point in the same direction as a given vector. And the technique is in fact exactly the same as it was in 2 dimensions. So find the unit vector in the same direction as V equals, let's just say 2I minus j minus k. 2I minus j minus k. All right, well, start by finding the magnitude. 2 squared plus negative 1 squared plus negative 1 squared. So it's going to be 4 square root of 6. All right. So then u, the unit vector, is equal to v over magnitude of v, which is equal to 2 over root 6 on the I minus 1 over root 6 j minus 1 over root 6 k. And this would be a way that many people would leave it, but it would be better if we could do it, if we could rationalize all the denominators. And you remember how that would go. You'd multiply the top and bottom each by root 6 here. So it'd be 2 root 6 over 6 I minus root 6 over 6 j minus root 6 over 6 k. And here these would cancel a little bit and we'd get root 6 over 3 root 6 over 3I root 6 over 6j root 6 over 6k. Okay, now one last thing to note is that dot products also work exactly the same way. Note. Dot products are very similar in 3D. And in particular, let's say that V equals AI bj plus ck, and W equals di plus ej plus fk. Then v dot w is equal to ad plus be plus cf. And v dot w is equal to still the magnitude of v times the magnitude of w times the cosine of the angle between them. So theta is still equal to cosine inverse of v dot w over magnitude of v magnitude of w. So as an example, find v dot w and find the angle between v and w. So one quick example, or we'll do two quick examples, one that works out neatly, one that works out less neatly. So let's say v equals I plus j. If any of the three components seems to be missing, oops, I plus j, that just means it's equal to 0. So 0 on the k. W equals negative I, let's say, plus j minus k. So then, when I'm finding the dot product, I often will find it useful to boil it down into its specific components here. 1, 1, 0 would be for the v. Negative 1, 1, negative 1 for the w. And then v dot w would equal 1 times negative 1 plus 1 times 1 plus 0 times negative 1, which would be negative 1 plus 1 plus 0 equals 0. So if the dot product is 0, then that means the same thing now as it meant before, and that in particular means that these are orthogonal. So the angle is 90 degrees. Now let's say we have v equals 2i plus 2j minus k. And w equals I plus 2j plus 3k. Now, we start again by finding the dot product, and the dot product, once again, I find it easier if I rewrite it each in terms of its components. V is equal to those, 2 to negative 1, W is equal to 1, 2, 3. So then V dot W is equal to 2 times 1 plus 2 times 2 plus negative 1 times 3, which equals 2 plus 4 is 6, minus 3 equals 3. Well, alright then, the dot product equals 3. It's not 0, so we can't jump to any conclusions like we did in part A. So now we have to figure out the magnitudes of the two vectors. So the magnitude of v is equal to the square root of 2 squared plus 2 squared plus negative 1 squared, which is equal to 4 plus 4 plus 1 is equal to square root of 9, which equals 3. Okay, good to know. Magnitude of w is equal to square root of 1 squared plus 2 squared plus 3 squared. that's going to be 1, make it 5, make it 14. So square root of 14. So then, if I want to find the theta, the cosine inverse of 3 divided by 3 root 14. Or in other words, cosine inverse of, I can cancel the 3's and it'd just be 1 over root 14. Which there's no point in rationalizing that, or even there wasn't any point in putting that in, except that it might save me a typo in my calculator. Because I'm just about to put it in here and see what I get. So 1 divided by square root of 14. I get 74.4986. So I'm going to say 74.5 degrees. Okay, so as you can see, it's a very similar calculation to what we would have done in the last section. And so 3 dimensions are not so very different from 2 dimensions in the arithmetic of vectors. The only extra part is a new component, the k component, which represents the z coordinate. All right, well, that's going to do it for this edition of Math 112. See you next time. Bye.